Here we see a steel part which consists out of rolled sections, but also has sections that are parametric, which have parametric depth. In tekla they are named in this way. In RFEM they are named differently. We also have concrete parts, slabs, columns. We also have some simple connections that are already modeled inside tekla. Also here where those parametric sections are connected, we have some simple connections already modeled. Okay, I take a look in the analytical part of this model, and I have prepared already, as I shown on this more simple model already, the analytical part. I can leave it open or minimize this window, and we can take a look at this model. We see here there are some releases. We see here there are some support conditions. Yeah, and with this model I will go to start my calculation. So the tekla engineer needs now some pre-design for this structure. He needs to know which sections I can use, and for this he transfers it to the RFEM structural engineer. We just import a new model from tekla structures, just as I shown before. We choose the analytical model, same settings as before, and the software is looking now for all the elements which are there, and I get the new model imported into RFEM. Let's take a brief look. We see here the releases, we see here the supports, we see all the cross sections that have been entered. We see here also that the parametric section was converted to the RFEM Duval naming, and I can start right away with this model with an analysis. For example, I create a few load cases, let's say self-weight, and we'll check the model and just run it with self-weight to see what happens. And as you see, we have results. We can see there is surface results, there is deflections, and everything seems to be modeled pretty decent, and it seems to be connected correctly. Okay, next my work as a structural engineer begins, and I start to add some bracings because the original design is without stiffening of the structure, and I need to have it, otherwise I won't be able to do a correct structural design. So I enter some tension only sections, I create new sections, some round sections with the material steel, and I just model in RFEM as I would if I would not have imported it from tekla. It is a original, or it is a real RFEM model. It is nothing else but if you would have built it yourself. So you don't have to do further exchanges. You can just work with it in your real environment as you like. Okay, we have now bracings, and now we need to continue with adding some loads. So we have load case self-weight. We fill in the loads. For example, we put in there a area load of 1 kilonewton per square meter in global or in local direction C of the area, and I use the cell area load generator where I just simply can select cells to describe the members that will be loaded. All members that are now orange will get loads from this area load. After the generation, I get some statistics. I can control, for example, the amount of the entire load, and I have now here 1 kilonewton per square meter distributed on my beams. The same thing I will do for the concrete slabs. Here it's more simple. I can just use a surface load and just apply it by clicking on the surfaces. First load case is done. We create a new load case, typically snow. And for this I can use a snow load generator, generate snow from Eurocode for flat roofs. You can select here your area, your region, where you are located. We can select Central Europe. We need to select then which snow zone we are. We can say zone 3. We need the altitude of the building, and we get the other parameters as well, topography type and coefficient for the Eurocode snow load generation. We need then to select the roof geometry, which is from the structure. We see the snow load on ground is it's quite high. Maybe we shouldn't use this zone. We used zone 2, so it's a little bit still quite high. Let's just use 1. So we have 0.9 kilonewton per square meter snow load on the ground. It will be created in the load case number 2, and by clicking on OK, I see I get 0.72 kilonewton per square meter as the resulting snow load on this building. I can use this information from the generator also for the slab, where I can just remember it. I copied it into clipboard, and with Ctrl V I can copy the magnitude into the aerial surface load dialog, and then I have the load also on the slab. Okay, next thing will be new load case for wind load. Wind load, there is also generators, but in general case of buildings you just will have to do it manually or semi-manually. You can maybe use for parts, you can use the wind load generators, and if they are of general shape, then you will have to do manual input. But it's not as difficult as you might think. I first hide the rest of the structures and show only my columns, and I create member loads, linear member loads in global direction X with the size of 2 kilonewton per meter in the main center columns and 1 kilonewton per meter at the edge columns. At the side where there is suction, I will have to reduce this wind load a little bit, and here I choose 1.25, and on the edge columns I use half of that value again, and this way I will create the simple wind load profile. You can either click on the columns or just use a window. Once I'm done with the members, I show all the structure again, and I finish off with the concrete part, and here I apply the wind loads on the lines of the slabs here and here, and another one on the top. So this is similar to what we have seen in earlier webinars in the last weeks. And just one brief load here and one more, and then I'm actually already done with the load input. Okay, with this we can start a calculation, or we can continue with the calculation. We need to create some combinations. I do this with the Eurocode combination module. Actually, it includes also other codes, not only Eurocodes. And we can select here one of the national annexes, or we can stay with the general Eurocode rules. Let's stay with the DIN code, for example. Ultimate limit state combinations I want to create. The load cases need to, oh, I just see I forgot to enter the live load. So I go back one more time and create one more load case, which is simple to do, live. And I need to apply some live loads on the grids here in the steel construction. It is pretty handy because I can use now the same cell generator as before. It still remembers the cells that I was using, but now I can just deselect the cells where I don't want to have any live loads. So within a few clicks, within a time of a few clicks, I'm done, and I say OK, and the load is distributed on the grids. We have 5 kilonewton per square meter, and the same thing I need to do also on the slab. Okay, but now I'm done with my load cases. I go back to RF Combi. I need to assign my actions to from the load cases. In this case, each load case resembles one action. Then I can assign the actions to action categories. This is what you exactly find in the Eurocode, all those categories, and you need to let the program know which action belongs to which action category. This is then just mechanical work, I would say. Live load we choose for office areas, snow load, smaller 1,000 meters, and the wind loads. With this, the software knows exactly which combination factors and safety factors to apply. We create the calculation. We create the combinations using the calculation, and we'll see here now all the combination factors. I can export those combinations and an additional summary in a overlapping combination to the main program RFEM. And here I see now load cases, load groups, and load combinations. And in the load combination, everything, every max min values of the entire calculation are included. It's like an envelope. With this, I'll do some simple design of the members. Actually, it's about time to do a update of the structure in tekla, because we already know that we will need some bracings, and this is a valuable information for the tekla engineer. and I update the tekla model by direct export. I select then the update option in the showing dialog. I can override the existing structure. I can append to an existing structure. That means if you have already sent a RFEM model to a tekla file, you can send another part of the structure or another building to the tekla file. You don't have to override, or maybe just if you go frame by frame or level by level, you can step by step update or append your structure. I want to update the existing structure. I don't worry about internal forces at the moment. I update coordinates, I update materials, sections, and thicknesses. By clicking OK, I start the update process, and it's done now, and I open the tekla model, and we can close now actually the analytical part, and we see here the bracings are updated automatically. At the same time, let's say I get a call from the architect or somebody else, and he tells me we have a major problem because we can't use this column here. It needs to disappear. There will be some opening here, and we can't use a column here. At the same time, we forgot to model the opening here in the surface slab. We need to have some opening here to be able to get up there with a stairway. So I create here a opening. Also, as an engineer, I know here I most likely need another beam to support this slab, and I enter another beam, create a new section, rectangular section, width 300 and depth maybe 600. Okay, made from concrete. Okay, and it will be a beam initially from here to here. I don't like that the beam is in the center of the slab. First of all, the forces will be different if they are eccentric, and second of all, I want to have it below the surface, so I edit the beam again and I make it into a rib, and I make it in such way that the eccentricity is calculated automatically by the software, and the beam is placed below the slab. Once I change the thickness of the slab, which I do now because I think we can get by with a less thick slab, it will automatically update the eccentricity of the beam. Okay, everything else is still here. I have my loads here, and I can immediately run the calculation. Okay, I will do some brief check of the steel sections. I start the RF Steel EC3 module, choose also the DIN National Annex, choose my load combination for design. I go through the input tables. I'm optimizing different sections. I can see in the background they are highlighted, which are the ones that I select are automatically highlighted, and I want to optimize all the beams. With the parametric section, I have the option also to automatically select which parameters I want to optimize. In this case, I only want to optimize the depth of the section. Okay, one more, maybe those top beams, and the columns I leave unchanged. And with this information, we start the analysis. For lateral immediate supports, I keep everything empty. I say member length is the buckling length, which I know is not quite okay, but for an initial design it should be not so bad. I have already second order analysis results. All I need to do is I would have to apply imperfections. With this I go into the analysis and it calculates the results of all the created load combinations, 13 of it all. You see it's an iterative process because it's second order and because we have tension only elements in there, so it needs more iterations. Now the optimization process is started and I get suitable cross sections, and then after that we do the final design of the of the beams and members. Still EC3 does a ultimate limit state check, a capacity check of the cross section, stability check, and also, if I set up correctly, serviceability check, as we have seen in earlier webinars. For those who haven't been part of the earlier webinars, they are up on our website or on the GoToWebinar website. All you need to do is basically register and then you can view them. We got now results and we see here the maximum design ratio. A good overview about the changes you can see in the cross-section table. And if I click here, I see those beams originally were 220, AGA 220 in RFEM, but in steel EC3 they are 200. And there are some changes also in the other beams. Okay, with this I can then update my RFEM model. I right-click in the table and I export all cross sections to RFEM, because now I'm still working in the design module, and once I found my correct sections I update the entire model and then the changes are in the real RFEM model. And once they are there, I can right away update also the tekla model. So let's do this. Direct export to tekla structures. I do as I did before. Update existing model. Same settings. I click OK, and we can go to tekla. Take some time and then the changes will be visible, and you see how everything changed. The opening is here, column is gone, the beam is here, the cross sections have been changed, and also even though the beams have been changed, the connections have been automatically updated. So no work was lost inside tekla while you were working with RFEM. So this is a good example how you can update your structure from RFEM to tekla and not lose any information. And I think that is a very good thing, because you can, for example, start with modeling your connections and then verify the section, and if a section should change, tekla automatically takes care of it. We see here also the plate was, the slab was changed, and the cross sections we have seen, but they are now of smaller size. Okay. Inside RFEM, maybe to top it off, we do a quick surface design in concrete, where I also select the German annex. I select the same combination and I do some reinforcement layout. I start the analysis, and the software will give me the required reinforcement for bending, shear, top, bottom, for the slabs. And the same way I could also design the members. And what we can do with the reinforcement, we cannot export it to tekla at the moment directly. We can reference, for example, a DXF file that we can export from RFEM. We have some companies now that start to do their own implementations. It means that we have the COM application also for reinforcement information, and we can get all these reinforcement values to tekla, and tekla has then the option also with the COM interface to create rebars, real rebars, not only theoretical reinforcement content, but also rebars from our results. But since every company has their own rules and standards how they want to do it, it's quite difficult for us to find a standard procedure, and therefore we're actually happy that we have this COM interface, because we can enable the users to do their own applications as they need it. And it's done quite often, also in the steel industry. At the end, I'd like to show you a few more things before we go on to some questions. For example, what we also can do is we can update the tekla model, the tekla database, with some results for internal forces. For example, I see this beam here, and if I update now the tekla model with my load group results, load group 7, I enable results. We will also write in the tekla model the results. So remember 17 kilonewton, and I go to tekla, and I find this beam. Also, which is important, it's still one piece. There's one cross beam, while in RFEM I have 1, 2, 3. So with this information set of member, I'm able to keep this beam as one unity. If I right click on the beam and select user defined attributes, I find here end conditions. And we remember maximum moment axes are differently in tekla. We take care of it. Major axis MC minus 17.82, and here we have the same value, also minus 17.82. If we check the axial force, we have here something like, or maybe we should look at the column, 40 or 75 here in the center. I select the center column, which is still one piece, and I get the result. So we have here 75 as a compression force.